Hello, Algebra 1. Well, today we're looking at 2.2b, and we're going to graph linear functions. So 2.2a was just finding out what linear functions were and realizing they're linear functions. But today we're going to graph them. And the big thing about today is not so much the graphing. I mean, we are going to graph, but we're going to really focus on discrete versus continuous data. Okay, so that's what we're going to look at today. And notice it's talking about a solution of a linear equation in two variables. Variables is an ordered pair x, y that makes an equation true. When you have all those different coordinates, you can plot them and it'll be a line. But we've got different sorts of data, and it often depends on how the problem is set up, what kind of information is in the problem. So for discrete domain, it's going to be a set of input values that consist of only certain numbers in an interval. And their example is integers from 1 to 5. Well, if you're talking about integers, you don't get to count the fractions in between. And they're saying from 1 to 5. So your domain here, your domain would be a list from 1, 2, 3, 4, and 5. And that's it. Discrete data doesn't count the spaces in between. It's going to be, just the specific numbers. Doesn't count everything in between. And some examples for discrete data, discrete domains might be like number of people. Tickets is a good one. It could be like, I don't know, just, actually technically like money. Technically, sometimes people will go half pennies and stuff, but typically people, tickets, money, that's all going to be discrete data where it's exact amounts. There's no fraction amounts is what I should get at. Now, continuous data is different. It consists of all numbers in an interval, okay? So if you're talking about all numbers from 1 to 5, that's going to be continuous domain. And we've kind of talked about that. To be continuous domain, you could use interval notation from 1 to 5, like that. And that says, everything in between. Or you could do an inequality, 1 to 5, like so. But yeah, you count everything in between. So some examples of that would be like time. Time, you can do half seconds. You can do, decimals of seconds. Time is continuous, okay? It doesn't care if it's a half a second or not. Also, if you're talking about like the weight of things, weight, you might think, oh, well, no, you can't be half a pound. Yeah, you can. You can be half a pound. It can be half a pound. There's lots of different ways that you can split up weight. Also, if you're like losing weight, well, you have a starting weight, you have an ending weight. You had to go through every weight in between to get there. Your body wouldn't just like jump over certain weights. So it's continuous. It's kind of interesting to think about this stuff. All right, so to graph discrete data, let's take a look here at their discrete data example here. They've got a linear function f of x equals 15.95x, and it represents the cost in dollars when you buy X tickets for a museum. Okay, so they're buying tickets for a museum. So yeah, tickets. This is going to be discrete. And class, keep in mind f of x is the same as y. Okay, so if that helps you to graph. to make it Y. That's what we'll do. All right, so it says each customer, oh, this is important. Each customer can buy a maximum of 4 tickets. So it says find the domain of the function. Well, since it's tickets, we're going to make a list. And it says you can buy a maximum of 4 tickets. So you could buy 4 tickets, but you could buy less. You could buy 3, 2, 1. Heck, you may say, I don't want to go to a museum. So you're going to buy 0 tickets. And then from there, it says, is the domain discrete or continuous? Well, you know, guess what? It told us up there, didn't it? That's kind of lame. But yeah, is the domain discrete or continuous? It's discrete. It's nothing in between, okay? Nothing in between. So no partial amounts. No partial amounts. That's usually how I'll say when it's discrete. No partial amounts. You can't buy half a ticket. If you want to write can't buy half a ticket, you can write that. Okay, now to graph this, your domain will just put in here 0, 1, 2, 3, 4. And we'll calculate the corresponding outputs and then graph them. 0 tickets, you ain't spending any money. 1 ticket, 15.95. 2 tickets, beep boop bop boop beep, in your calculator. You get, oh, well, that makes sense. 16 would be 32, but then it's a dime less. Okay, so 31.90, yeah. 15.95 times 3. 3 tickets is going to cost $47.85. And 15.95 times 4 tickets, $63.80. Okay, now to graph this, we weren't given intervals to go by. So for my tickets, which is my X values, okay, I'm going to have to go from 0 to 4. And I'll just make it easy on myself and just go by ones. 1, 2, 3, 4, 5. But then for my outputs, the money that I've spent, I got to get up to $63.80. Okay, so I think I'll just go by tens. I think that'll get me there. On these, I often have to get a nice interval. I'll often try something and then have to erase it and go back and fix it to realize that I needed to make my interval bigger, the numbers bigger to make it all fit. But going by tens will fit the data nice. It will. So then we just plot these. Now notice, because these are like in between amounts, we just want to be as accurate as possible. 0, 0, that's pretty easy. But 1 and 15.95, that's going to be a little over halfway to 20. For 2, 31.9, that's going to be pretty close to 30. For 3 tickets, 47.85. So that's going to be over halfway to 50. Oh, wait, 4 tickets. 3 tickets. Whoops. Okay, 3 tickets. 47. Okay, and then for 4 tickets, we got to go 63.80. So that is less than halfway. 4 tickets, 63.80. Okay, yeah, less than halfway. All right. Oh man, okay, so no, I'm up here. I was like, that doesn't look right, because I'm less than halfway to 70. I'm silly. Okay, there we go. It should be linear. Our data should be linear. Sorry about that. Spacing out some. All right, so now class, here's the thing. We could not buy partial tickets, so we leave the points as they are. Okay. Okay, now let's flip it over and look at an example of continuous data. And when I first read this problem, I was like, this is not continuous, this is discrete. But then I realized, oh, I could eat half a bar. So anyway, that's the difference here. So a cereal bar contains 130 calories. The number C of calories consumed is a function of the number B of bars eaten. Does this situation represent a linear function? And it certainly does. Yeah, the calories are going to be equal to 130 times the number of bars. Think of C as Y and B as X, and you can see, yeah, this is Y equals MX plus B. This works out. This is good. Yeah, and so it's linear. So there's no extra like operations or anything like that. No extra stuff going on with the X's or Y's. All right, next up, they want us to find the domain of the function. Now, I've already determined that this is going to be continuous because we can eat half a bar, but we need to think about the specifics of that. How many bars could what's the minimum that we could eat? Well, the minimum is going to be 0. But then we could get a half bar. We could eat a full bar. We could eat 1.5 bars, 1 3/4 bars. We can get all these in betweens. And here's what's really wacky. It doesn't tell us an upper limit. We're starting at 0, but you could devote your life to eating bars and make it infinity. I mean, yeah, you could just eat bars and just keep going, I guess. Yeah, just keep going. So it's going to be from 0 to infinity. Or if you want to do inequalities, you'd say B is greater than or equal to 0. So yeah, it's totally continuous because partial bars are possible. Yeah, isn't that interesting? Okay, so to graph this, now what confuses people a little bit, we're going to write 130B here. That's what we're going to calculate to get the calories. To graph this, we need some sample points to then connect. So don't mistake what I'm going to write here as being discrete data. We just got to get some sample points first. So we've got, we'll start at 0. We'll go 1, 2, 3, 4. And we'll calculate what each of these is. If you eat 1 bar, 130 calories. 2 bars, 260 calories. 3 bars, 390 calories. 4 bars, 520. Okay. And then we graph this, but we want to get our spacing right. I think I'll just go by 1s across here. But up here, I really want to get all this data graphed on here. So, and my first data point, aside from 0, 0, is 1, 130, okay? So I'm got to go up to 520. So I think what I'll do is I'll just go by hundreds. 100, 200, 300, 400, 500, 600. We'll just go by hundreds. And again, you're just going to plot these the best you can. 0, 0 is pretty easy. 340 is less than halfway between. 260 is more than halfway between. 390, that's getting close to 400. And 520, that's less than halfway between 5 and 6, less than halfway. All right, and now class, because we can count partial amounts, we're going to use a straight edge to connect these dots. They should line up pretty good, and they do pretty good. and we're going to connect them. Now notice I'm not going to put a line or an arrow going back this way, and I'm not going to go into the negatives because it doesn't make sense to eat negative bars. We started at 0, 0. But going the other way, I'm going to put, that's right, I'm going to put an arrow because we can keep eating bars for eternity. Oh, I forgot to label number of bars, calories. It's important to label those on word problems. All right. So yeah, partial bars are possible. Again, class, take a look at this. This does not mean it's discrete data. That just gave us some sample points, and then we connected them to make it continuous. All right, for these examples down here, we've got our discrete example. We've got our continuous example, and then our job is to think up what these graphs are about. And I used apples in my classes today. So this was a number of people. And this was a number of apples. So basically what I thought was apples in a barrel. And as each person comes up, they take an apple. And so that would be data there. Notice they're just taking an apple, so there's no partial apples. They're just taking the apples away. But then if we wanted to think of maybe like you're making pies or something like that, what you could think of for continuous stuff is like time. You could do number of hours. And then maybe there's like apples on a tree. Or no, that doesn't make sense. There could be like pounds of apples. Pounds of apples. So maybe you got these processed apples, and as time goes by, the more and more of the processed apples are being used up. Maybe they're making pies or something like that. So that could be continuous apples. The pounds can be continuous, the hours can be continuous, and just the amounts of apple stuff is just slowly decreasing as long as you're talking about the weight. All right, there you have it. Thanks a lot.